Okay, and then we have a chain line down here, or the hidden feature. Okay, and then where the neutral axis now is, the neutral axis is now a dot. Okay, neutral axis. And then we put in our uh, element H, right? And this over here is our element K. Okay, I need more space for that. So over here, this is our element K. Then we put in the associated forces. This is 150 and 50. Okay? And then this is your 200 pounds. And then you have your 150 coming towards us. Okay? You got 150 coming towards us. Okay. Okay. So anything else? That's all. So now when you look at the front view, right, you have to analyze all this. Okay, you have to analyze all this load. Now we don't need to do VZ because we already got from the previous view already. We know that VZ, right? We already know that VZ is equal to 0. We have done that already. Okay. Now, interesting thing is here, right? We know that the 200, right? The 200 that you see has a perpendicular distance, right? And this perpendicular distance is 10 inch, right? So now the question is the 200 pounds inducing a torque, okay, in the x-axis, or a moment, or we can call it mx, okay? And we know that Tx is equal to force multiplied by radius, and mx is equal to force multiplied by perpendicular distance. A lot of times students get confused, and I also get confused, is the radius is also in fact equal to the perpendicular distance, right? So whether it is a torque or moment is dependent on the deformation of the neutral axis. Okay, so let me show you in this case, right, what the 200 pounds could do. If we were to look at the 200 pounds, okay, it's going to induce a deformation this way, right? So this is the deformation. And the neutral axis during deformation is still fixed, right? It did not move at all, right? So this is important again. This is number 8. Okay, number 8 point. When the deformation, or when the neutral axis is still fixed or at the same position after loading, okay, the applied load will induce a torque. Okay, so for this case, torque in the x-axis, okay, is equal to 200 multiplied by 10, so it's equal to 2,000 pound-inch, and the rotation is going in this way. Okay, so when you look at the formula, the shear stress is equal to Tx over the polar moment of area multiplied by radius. Okay, the shear stress at element H is equal to the shear stress at element K, and it's not equal to 0. In fact, the shear stress will be at its what? Maximum of element H and K, because R is the maximum. Okay. So this is basically the points that you have to take note, okay, that you should have in your summary sheet in compound loading. Okay, and the term test 2, I will test you until you sketch the element. Okay, I'm not going to test you on 2D and 3D mold circle yet. It's not fair. It's too much for all of you. Oh, by the way, this week I forget to make an announcement. I'll put on Avenue to Learn. There's no quiz this week. I want you to focus on your homework and study on your term test. Okay. Lucia, is this okay? Is this summary okay for you? Or you're expecting more? Yeah, okay, okay. I hope it clarifies more stuff for you all than more confusion. Okay. Now, compound loading, by the way, compound loading structures like this is not straightforward. Okay, but if you follow the rules that are given you, okay, you should be fine. Okay, next question. Anyone, please. Don't be shy. Come on.
May I ask a question from set 7 homework?
Yeah, you definitely can. Homework 7.
Homework 7, number 4.
Yes.
So I was just confused. How did the half H2 come from at the when it's solving for area?
Wait, where is half H2?
It's when it's solving the area, like the second line, it says A equal to a half H2 minus Y.
Okay, let's. Yeah, I don't know why also. Okay, so let's. As I said, these are just checkpoint. Don't figure out. Use the method that I teach you. That's the best way. Okay. Okay. We'll take this whole thing again. And wait. My computer just crap out again. Our So over here you have to integrate, right? It's a lot of integration. Hold on. Okay. So the question asks why the area is half h2 minus y. I don't know why. Okay. But let's focus on the right flange, like what I taught you before. Okay, right flange. So you have a vertical okay. Then we know that the green is our centroid, right? So we will call this distance from here to here. Oh, do apologize. This is h/2. And then we know that we want to find, okay, we are going to call this point over here, right? This is our y. So y is this is our variable, right? So if this is the area that we are going to consider, right? That's the area we are going to consider. So they have to calculate the area because they want to find what is A is equal to, or Q, what am I doing? Q is equal to A y bar. Okay. So the thickness, the width is T, I think they call it T2 over here. Yeah, T2. And the depth, right? The height is h/2 minus by y. Okay, so that is the area. And then the y bar is h/2 plus by y multiplied by half. Okay. Now let's answer the question. So the area you see is T2 h/2 minus by y. Okay. So is the same that what you see over here. Am I right? Okay. And then the y
Yeah.
bar, yeah, the y bar is here and it's the same. So if we were to calculate our Q now, right, is equal to T2/2, right? H squared over 4 minus by y squared. Is it the same? Yeah, it's the same. Does that make sense to you?
Yeah, it makes sense now.
Yeah.
Yeah.
So again, they did not do all this, right? They take it from the bottom. Now, why I did this is we applied the rules that the first moment of area cannot cross the what? Centroid. Yes or no? They do this, they let the first moment of area cross the centroid. So that's why the rules I gave you, you have to apply them. Okay, and then the answer is going to be always be the same. Okay, it will not be different at all. Why? I've tested in too many problem already. Okay, I hope that answer your question.